Welcome back. In this video, we're going to take that concept of our MO diagrams and apply it to pi systems. So far, we've been talking about S block elements, right? And there's really only two ways to bring two S orbitals together, which is to say, I've got that end-to-end sigma overlap. That's why all of our previous molecular orbital configurations had sigma 1s, sigma 1s star, sigma 2s, right? That sigma there told you the type of bond we were making. Now we start to bring in our p orbitals, however, we've got two different ways that we can combine. We can do a sigma overlap, right, an end-to-end overlap, or we can do our pi overlap, our side-to-side overlap. Now both of these are going to have associated molecular orbitals. We can see up here that we've got our sigma 2p, we get this big bonding area in the middle. Again, we still got a node, right, two nodes because we had two p orbitals to start with, and our little sort of not participatory orbital lobes out on the end. And we've got our anti-bonding where, again, we put a node right in the middle, and most of the electron densities point away from one another. We see something similar for our pi overlap. Right? This is that sort of more globular version of the pi bond that I sometimes like to use. Right? We see we've got that side-to-side overlap above and below that internuclear axis. In the anti-bonding p orbital, you can see we've got a lot of space in there as these all, again, sort of bend away from each other. The electron density is not between the two nuclei, right? That's the important bit there. But this gives us an idea of how we can combine these. If I take two p orbitals, I'm going to end up with, again, one anti-bonding and one bonding, whether I'm doing a sigma bond or a pi bond, right? So we always have to have that orbital conservation going on. Now, of course, we have more than one p orbital. Right? So how does that impact, along with our s orbitals, what's going on with our molecular orbitals? Let's take a look. So here's an example of what we might see for some of our p block elements, specifically oxygen, fluorine, or neon. Now, you'll see right down here at the bottom that these atoms all, of course, have s electrons. If we look at oxygen, the atomic orbital configuration for it is 1s2, 2s2, 2p4, right? So we can ignore our core electrons, but we have 2 s electrons and 4 p electrons. So we'd start putting those together. So I still need to have this s block just like we had for our previous set of elements. But we've also got this upper bit with the p orbitals. Let's blow this up a little bit and take a look at it. All right, so here we can see that we've put this together and we've got this diamond shape. It looks a little more complex. Now, why is that? Well, if I've got two p orbitals, there's only one way that they can make a sigma bond. Right? There's only one end-to-end overlap that's possible. So I've got one molecular orbital position where it gives me a bonding interaction that's a sigma bond. So this is my single sigma 2p, because notice it's going to be formed not from s orbitals overlapping, but from our p orbitals overlapping. All right? There we go. Now, p orbitals can also interact in a couple different ways, which is to say I can form pi bonds. Right? And we talked about the fact that I can be sort of in the plane of the page, or I could be in front and in back of the page and have that end-to-end overlap. Right? This is going to be on the other side of the internuclear axis. So, because I've got two different orientations in which the p orbitals can overlap, I've got not one, but two boxes in my molecular orbital diagram for my bonding, and therefore anti-bonding, pi bond interactions. Right, so this gives us this shape. Now, we tend to form our sigma bond first, right? Then we form our pi bond second, so our sigma bond's the lower energy, followed by the pi bond, and then since it always mirrors itself, our pi star, right, our anti-bonding pi bonds, or our anti-bonding pi orbitals, are actually lower energy than our anti-bonding sigma orbitals. So that's going to give us this type of shape. Now note here that we're saying that this is going to be particularly applicable to things like oxygen, fluorine, and neon. Right? That's because for these atoms, they are small, and their s and p orbitals are fairly different in energy. Right? It's because we've got a lot of electron density. If we think about oxygen, oxygen's going to have those 4p electrons, right? 4p electrons means that I'm going to fill up a lot of this up here, so I'm going to have a lot of electron density here, and that means that it's going to not play well with these s orbitals that are down below. All right, so we have no mixing going on here. So we got repulsion there, so they're going to remain very distinctly different. Now, on the other hand, we can look at some smaller, less electronegative atoms. Let's look at an example of that. All right, now here's an example where we could look at something like carbon or nitrogen. All right, now carbon and nitrogen are not as electronegative and not as electron dense as oxygen, fluorine, or neon are. Now, because of this, there's actually better overlap between our S block and our P block. Now, what does this mean? This means that basically the S block gets to steal some of the electron density from the P block. So you'll notice that whereas before I had this nice regular diamond shape down here, actually let me, this square that went around, both of these have decreased. They've gone down. So now I have something that looks a little bit more like a baseball diamond, by way of example. Where does that electron density come from? Well, it's come from the 2p level. So you notice that both of my sigma 2p's have gone up in energy to the point where they're now actually both higher in energy than my pi bonds, right, or my pi orbitals. So in this case, our s and p orbitals are going to interact. There's going to be some mixing, some overlap. So you kind of think of it as like a sharing of space, right? So if the s orbitals get that space, the p orbitals lose that space, and that's going to lower the energy of our sigma 2s's, and it's going to raise the energy of our sigma 2p's. All right, so that's what's going to happen. We're going to have slightly different pattern of our boxes here. So how do we remember this? How do we remember when we have mixing versus when we don't have mixing? Let's compare the two side by side. If we compare these two side by side, here we've got no mixing over on the left, and we've got our mixing over on the right, as we see there and there. What can we do to try to keep these separate, to remember which one goes with which? Well, I like to think of the fact that oxygen, fluorine, and neon are all bigger atoms in that they have more electrons, right? So we have more electrons, we've got more electronegativity, we've got more ability to hold on to electrons, so we kind of have more power, if you will, right? So if you have more power, you control the whole block, right? You got everything, it's just one nice square. And that's really an ugly square. Let's try that again. Bam, 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 bam. We own the whole block. On the other hand, if you don't have that much power, you kind of have to give some to get some. So our p orbitals are going to end up giving some, and our s orbitals are going to end up getting some. So our sigma 2p and sigma star 2p go up in energy. Our sigma star 2s and sigma 2s go down in energy. All right, that's going to happen with our smaller or less electronegative members of the second period here, carbon and nitrogen. All right, now here we're still only talking about diatomic homonuclear species, so don't worry about sort of, well, how does this apply to every molecule ever? We're not going to get into that. Here we're just talking about pure elements, O2, F2, Ne2, C2, N2, etc. Mixing versus no mixing. Just in case you're still having trouble connecting what that mixing means and how it connects to these two different diagrams, I'm going to draw a couple lines here to really try to show what's happening. All right, so here I've got my 2s, sigma 2s, and my sigma star 2s, and you can see that those both decrease energy, right? They're both going to go down. My sigma 2p and my sigma star 2p are both going to go up in energy. All right, my pi bonds here, my pi bonds here stay at the same energy. They don't move, right? So this is really just moving the sigma 2s and the sigma 2p and doing a little mixing there since these are smaller and able to mix and share some of their electron density more efficiently. That takes us to the end of this. Come back next time as we look at some slightly different examples and start bringing this into heteronuclear molecular orbital diagrams. Till then.